Hello friends, in today's class let us study the machine architecture of SIC machine, that is simplified instructional computer. After this topic we will study the architecture of SIC XE machine also. In both of these machines we have to discuss seven or six or seven mm, concepts. First one is memory, second one is registers, third is data formats, fourth is instruction formats, fifth is addressing modes, sixth is instruction set, seventh is input and output operations. So these seven steps or seven concepts we have to discuss in SIC XE machine also. So first we will study these seven concepts in SIC. In that first one is memory. So memory in SIC machine consists of 8-bit bytes. Of course memory, 1 byte is nothing but 8 bits, and all memory is addressed as or referred as here byte memory or byte addresses. So memory consists of bytes here, and any three consecutive or continuous 3 bytes will form a word, that is nothing but 24 bits. So 8 into 3, 24 bits. A word is nothing but 3 bytes or 24 bits, and all addresses of these memory locations on SIC are byte addresses only. So words are addressed by the location of their lowest numbered byte. So it means that, for example, here one word is there. So this word is nothing but a consecutive 3 bytes, first byte, second byte and third byte. So second word is also having 3 bytes, fourth byte, fifth byte and sixth byte. So how to address these words, or how to address these memory locations here? All addresses on SIC are byte addresses. Words are addressed by the location of their lowest numbered byte. It means in this word this word is divided into 3 bytes, and 3 bytes are divided into 8 bits. In each bit, each byte there are 8 bits are here. So totally 24 bits are here. So if I want to address or access this word, I have to access through the lowest numbered byte of this word. So 1, 2 and 3. Among these 3 bytes, which one is the lowest byte? That is 1. So this entire word is addressed with the address 1. And here in this second word, again there are 3 bytes are there. So first byte address is 4, second byte address is 5, third byte address is 6. Then how to address this second word? Again with the lowest numbered byte only we can address this second word. So lowest number is 4 here. So 4 is a address of this entire word. So address of this word is 1, address of this word is 4. So there are total 32,768 bytes in the computer memory. That is simply, you just remember, the memory of SIC machine is 2 to the power 15 bytes. Okay, 2 to the power 16 bytes. Second one is registers. Sometimes in your exam it will be asked for 7 marks, and sometimes the question may be for an entire architecture of SIC machine also for 10 marks. But sometimes they may ask only registers for 7 marks also. No. Okay, so there are 5 registers in SIC machine which have special uses. Each register is of length 24 bits. It means that each register contains 24 bits, means its length is a word or its length is 3 bytes. Here there are 5 registers are there. Each and every register has its own purpose and special use. So these registers are in short we can call them as A, X, L, P, C and SW. So these A, X, L, P, C and SW are called as mnemonic of those registers. And these registers have their number also, like our roll number. These registers also have their numbers. So these numbers are very very important. We cannot neglect or ignore them, because these numbers are very very useful for us in future to solve the problems. Okay, so first register is A register. A is nothing but accumulator register. Accumulator register, it is used for arithmetic operations like addition, subtraction, multiplication and division, and its length is of course 24 bits as already we told, and its number is 0. Accumulator register number is 0 and it is used for arithmetic operations like addition, subtraction, division and multiplication. Second register is X, its number is 1. Its special use is used for addressing. Its name is index register. So first one was accumulator register, second one is index register. Index register is used for addressing. Third register is L and its number is 2. It is called as linkage register. The jump to subroutine instruction is nothing but a JSUB instruction. Jump to subroutine instruction stores the return address in this register. See, jump to subroutine instruction we will study in next topics. There we will understand better. So what is this return address and all those things. Now just you remember that linkage register stores the return address. Okay, and PC is called as a program counter register. Program counter register, its number is 8. Program counter register contains the address of the next instruction to be fetched for execution, or it stores the next instruction, address of next instruction to be executed in the program. So last register is SW register. Its number is 9. SW stands for status word. So it contains a variety of information, including a special information called as condition code CC. Okay, so this condition code is nothing but, so whenever we compare two registers or two memory locations or two registers with the help of relational operators like less than, greater than, less than or equal to, greater than or equal to, or equal to, or not equal to. So such kind of relational operators if we use to compare the content of two registers, at that time the result will be obviously in terms of boolean, either true or false. To store that result we will use this condition code. Okay, we will study this in future in detail, don't worry. Now the basic 5 registers of SIC machines are A, X, L, PC, SW. A is a accumulator register for arithmetic operations and its number is 0. X is a index register used for addressing and its number is 1. L is a linkage register which is used to store the return address and its number is 2. PC is a program counter which is used to store the address of a next instruction to be executed in our program and its number is 8. SW is a status word register which contains the variety of information along with the condition code, and its number is 9. Next concept is data formats. Okay, data formats. In what type of format we can store the data in a SIC machine, or what type of data we can store in a SIC machine. So of course we can store integers, integer type of data. Integers are stored as 24-bit binary numbers. 24-bit binary numbers, it means that 24-bit, it means 24 bits means it is almost 3 bytes and one word, of course. So here in SIC machine, integers are stored as 24-bit binary numbers, and 2's complement representation is also used for to represent the negative values. 2's complement representation is used for negative values, and characters also we can store here using 8-bit ASCII codes. So of course characters require 1 byte. 1 byte is nothing but 8-bit ASCII codes, and there is no floating point hardware on a standard version of this SIC, so we cannot store floating point values here. So finally, on SIC machine we can store only integer types of values. It may be positive or it may be negative. If it is negative, 2's complement will be used here, and integers will be stored in the form of 24-bit binary numbers, and characters are also used in the form of 8-bit ASCII values or ASCII codes. But we cannot store the floating point numbers because there is no any floating point hardware on our standard SIC machine. Next concept is instruction format. So in SIC machine there is only one instruction format is there. All instructions will be in this same format or same syntax. So all instructions on SIC have the following 24-bit format. These all instructions will be compulsorily in this 24-bit format only. What are those instructions and what are those formats, and what are those bits reserved for other the different components or parts. So among 24 bits, first 8 bits are reserved for upcode. We will study and we will understand what is this upcode in later. Don't worry, it is nothing but it is operational code. We will see this one operational code later. Okay, so first 8-bit are required or reserved to store upcode. Next 1 bit is reserved to store the X, and last 15 bits are reserved to store the address. So here X is nothing but it is a flag bit. So you can observe here, this is not a capital X, it is a small letter x or a lowercase x. Capital X is nothing but it is a register, index register, but this is small letter x is a flag bit. X is used to indicate the indexed addressing mode. In the next concept we are going to study some addressing modes, different types of addressing modes. There one addressing mode is there, that is called as indexed addressing mode. To indicate that indexed addressing mode, we have to use this flag bit. So if this flag bit X value is 1, then it means that our instruction is used indexed addressing mode. If X value is 0, then in addressing mode, if X value is 0, then indexed addressing mode is not used in our instruction. That is the main purpose of this small letter X. So first 8 bits are for opcode, next 1 bit for indexed addressing mode, to indicate whether indexed addressing mode we have used in our instruction or not, and the next 15 bits are used to store the address. In next class we will see how to find out the address. Okay. Next concept is addressing modes. There are two addressing modes in SIC machine, and these two addressing modes are indicated by the setting or assigning the value 1 to these flag bit X in the instruction. So following table shows how this table shows how this target address or effective address is calculated from the address given in the instructions. So here in this instructions or this calculation or in this equation, here I have written one register X in a parenthesis. Okay, these parentheses are nothing but they are used to indicate the contents of a particular register or a memory location. For example, X represents the contents of register X. Mode is direct addressing mode, and how to indicate that direct addressing mode by using X equal to 0. And target address calculation, target address is equal to address. Okay, so simply how to calculate this target address, whatever the address was there, the same address will be target address. We will study what is target address, these all things, don't worry. Okay, so if you are using direct addressing mode, then X value will be 0, and target address for direct addressing mode, how to calculate target address, thus whatever the address was there, the same address will be target address. And the second addressing mode is indexed addressing mode. How to indicate this indexed addressing mode we have used in our instruction by assigning 1 or by setting this flag bit X. If X value is 1, then it is indexed addressing mode. And the target address, how to calculate, so address plus content of the register X. So it means say this time we cannot only take the original address as a target address, we should take the address plus we have to add the content of the register X. Content of the register X means this X is a index register. The content of this index register will be added to this address, then we will get the target address. So here one example is there. Here one example is there for direct addressing mode. Example, this is the instruction LDA 10. In the place of this 10 there may be any other operand like return address or 0 or length, like anything may be present here. Okay, this LDA opcode is 00. So this 0 is represented in 4 bits binary, and this 0 is also represented in 4 bits binary. So totally 8 bits are there. So this complete opcode and these complete 8 bits are filled now. Now next, X is 0 here. If X is 0 means we are using direct addressing mode here. Okay, and whatever the address was there, it will be taken as a target address here. So, okay, in this means the address of 10 operand in our program, whatever the address of this 10 will be there, it will be taken as a address here. That is for here just we have assumed that the address of 10 is 1000. So this 1000 is represented in 15 bits. So always since there are only 15 bits are there for address field, we have to start from right side. So last 0 is represented with 4 bits, this 0 is represented with 4 bits, and this 0 is also represented with 4 bits. So 12 bits are filled. Now the remaining 3 bits we have to fill, and this 1 is represented with only rightmost 3 bits, that is 0 0 1. So this is how we have to fill these all bits of this instruction: opcode, x, and address. Opcode is opcode is going to occupy 8 bits, flag bit x is occupying 1 bit, address is occupying 15 bits. So 8 bit of opcode and 1 bit of flag bit and 15 bit of address. This is for direct addressing mode. Okay, see here we are calculating effective address. Effective address is also called as target address, and here directly we have assumed that its value is 1000. So directly 1000 directly address is taken as a target address. There content of the address 1000 is loaded into the accumulator register. Second example is indexed addressing mode. Example instruction example is stch buffer comma x store character. It is store character instruction. We will study these instructions later. Okay, here opcode of stch is 54. So 5 is represented in binary as 0101, 4 is represented as 014000. So total 8 bits of opcode field is filled now, and x is 1 here. It means that here we are using indexed addressing mode, and here address is again considered as 1000. Address of buffer is considered as 1000. So 1000 is filled as 15 bits of address. And to find out effective address or target address, we have to take address and then we have to add the content of indexing register, index register x. So 1000 plus content of the index register x, the accumulator content plus the accumulator content, the character is loaded to the effective address. So next concept is, sixth concept is instruction set. It is nothing but a set of instructions what we can use in a SIC machine. Since it is called as a simplified instructional computer, there are only less number of instructions on a SIC machine with which we can perform some simple tasks. Instruction set SIC provides sufficient instructions for most simple task. Load and store registers are there: LDA, LDX, store, then store X, etc. Load and store instructions are there, and integer arithmetic operations are there. It means that addition, subtraction, multiplication, division we can perform. All arithmetic operations involve register A, because A is accumulator register with 24 bits and a word in memory. Okay, and comparison, compare instruction, COMP instruction compares the value in a register A with a word in a memory. This instruction sets a condition code CC to indicate the result less than, equal, or greater than. As I already told, CC is used to store the these values or results of less than, equal, or greater than. And then conditional jump instructions are there. Conditional jump means jump only if it is less than, jump only if it is equal, jump only if it is greater than, like this. Conditional jump instruction JLT, JEQ, JGT can test the setting of CC and jump accordingly. Okay, and here JLTM, JEQM, JGTM, this is the format of JLT instructions. Okay, here PC is nothing but program counter which stores the address of next instruction to be executed. So here memory is loaded into this PC if CC is set to less than. If CC value is less than, then memory will be stored into the PC, and if CC is equal, then memory is again stored into PC. Then if CC is greater than, then again memory is stored into PC. So these are the movement of data from memory to registers, memory to registers, memory to registers. Okay, we will see them in detail in next topics, don't worry. Then some subroutine linkage instructions are there, like jump to subroutine and return from subroutine. JSub is jumps to the subroutine, placing the return address in the register L, that is linkage register. Return from subroutine, it returns the control by jumping to the address contained in the register L. And last is input and output operations. Input and output operations are performed by transferring one byte at a time to the rightmost 8 bits of register A, or from the rightmost 8 bits of register A. So input and output operations are easily performed in SIC machine just by transferring 1 byte of data, 1 byte of data at a time to the rightmost 8 bits of register A, or from the register A to memory. Okay, so input and output operations are performed by transferring 1 byte of data at a time to or from the rightmost 8 bits of register A. You have to note here, each register is of 24 bits in a length. So leftmost 8 bit and middle 8 bit cannot be touched, only rightmost 8 bits will be transferred to register A or from the register A. So if these data moves, then it is called as input and output operations. And along with these input output operations, we have one more instruction to test whether the input output devices are ready to receive and ready to send the data. That instruction is TD instruction, that is test device instruction. This instruction tests or checks whether that addressed device, it may be input or output device, so this device is ready to send the data. If it is input device, so then it is key, suppose for example it may be mouse or it may be keyboard. This data, whether it is ready to send the data to the processor or monitor screen, then it will be indicated as a greater than symbol. Or receive the data, for example output device like printer or monitor screen, they are ready to display and they are ready to print the data from memory, it means, or from keyboard or any memory device also, whether they are ready to receive the data. So then if they are ready to receive the data, then it is indicated by the less than. Receive operation is indicated by less than, and send operation is indicated by greater than a byte of data. And if the condition code is set to indicate the result of this test, and the setting of less than means that device is ready to send or receive, and if the symbol is equal or CC value is equal, means that in that device is not ready. And a program that wants to transfer the data must wait until the device is ready, then execute the read data or write data. Even though the device is ready to send the data or to receive the data, after that, if once that device is ready, at that time only we can perform either read data or write data instruction. So here TD, RD and WD we have to execute the instructions. So we have to execute this RD and WD instructions only based on the value of CC. Okay, if CC is less than, then it is ready to receive the input, and if CC is greater than, then it is ready to write the data to the output device. In the next class, we will study the architecture of next machine, that is SIC XC machine.